Welcome to this 16th online lecture of the course, Engineering Thermodynamics. So, in this particular lecture, we will now continue our discussion on the throttling process because in the previous lecture, I have already talked about different applications of the steady flow energy equation, and that I have told you for different type of devices. For example, for our heat exchanger, turbine, pump, nozzle, diffuser, etc. And in this particular series, we were actually doing our discussion on another specific type of device which we have called as a throttle, and the process inside the throttle we call either as throttling process or expansion process. Okay, so throttle is also an example of a steady state process. So what we are having in case of throttle, we are having some pipe, and inside this flow passage actually we are having sudden contraction, sudden restriction to the flow. Okay, so because of this sudden restriction, what will be happening if I take 2 points, one on the upstream, I am calling this as say inlet point I, and 1 point if I take on the downstream of this particular restriction, I am calling this point as nothing but my point O. Okay. After that, what I was saying that the flow of fluid is happening through this, and obviously if at this point I have pressure Pi, enthalpy Hi, if at the outlet point I am getting pressure Po and enthalpy HO, so my PO will be very less in comparison to that of Pi. Okay, so what we are basically doing, we are fixing our upstream pressure, and for fixed upstream pressure, because of the restriction, there will be some pressure loss. So we are trying to find out that how much pressure loss we are having. Okay, so over here we have seen that instead of Pi, I have got some another pressure Po, which is less in comparison to that of Pi. Okay. Now, the process of throttle, I have already told you that in this particular process, we will be having no work done. Okay, and at the same point of time, we are not having any heat interaction. So, QCV through this control volume is also actually equal to 0. Okay. So now, if we try to apply our steady flow energy equation, we have already seen that QCV, our Q dot CV is 0 minus W dot CV is once again 0 over here. Then we were only having the term. So if say I say M dot is the mass flow rate of the fluid which is passing through this throttling device. So I'll be having M dot into fluid is coming with enthalpy Hi. Once again, I am considering kinetic energy and potential energy change for this particular throttling device as negligible. Okay, minus M dot into HO is equal to 0. So from here you will be finding that Hi is equal to HO. So if Hi is equal to HO, it means throttling process is nothing but during this entire throttling process, it means our enthalpy is remaining constant. If our enthalpy is remaining constant, I can call this process as nothing but my isenthalpic process. Okay, so this is a process where our enthalpy is remaining constant. So that's why I can call this particular process as isenthalpic process. Okay, so now what will be happening? I have already told you that our Hi is equal to HO, and we know that H is nothing but U. So it will be Ui plus Pi into Vi. That will be equal to UO. All of you please mute your microphone. So we will be having UO plus PO into VO. Okay, so that we will be getting over here. Now, one important point I would like to highlight over here. The point is that in this particular case, what is happening? Our this particular PO is less. So PO is very less in comparison to, or I should say in terms of comparison I am doing. So it is actually small in comparison to Pi. Okay, so it is small in comparison to Pi. So if it is less, in that case, what we have to do, this particular specific volume and internal energy of the fluid has to increase at the outlet. Okay, so ultimately we will be finding that we will be having a significant increase of specific volume in order to make this balance complete, in order to make the process isenthalpic. Okay. So what we are saying that if specific volume has to increase, in that case, what will be happening? We will be finding that in our throttling process, if substance is entering into the liquid phase, it will be actually vaporizing. Okay. So if it will be vaporize, if it vaporizes, then only what will be happening, our specific volume of the substance will be increasing significantly. Okay, because in the liquid state, what we are having nothing but a specific volume is almost constant, because liquids are of incompressible nature and the density is not changing. Okay, so if you have to increase the specific volume by significant amount, it means if we are considering that at the inlet of the throttle I have a liquid, that liquid has to actually vaporize. Okay, so it means that while our liquid is vaporizing, in this particular case, what happens, while we are having decrease of pressure, along with decrease of pressure, temperature also decreases. Okay, so this situation will be happening because while pressure is decreasing, at that time temperature of the substance will also decrease. So that's why temperature of substance at the outlet will be less in comparison to temperature of substance at the inlet. But that is something which will be only happening if we are having some liquid at the inlet, and that liquid is then actually vaporizing in order to make the energy balance or enthalpy balance same. Okay. However, if we are having any other kind of gas, for example, if I say air, and if I consider air under the condition of ideal gas equation, so if air is following the behavior of ideal gas, under this condition, what will be happening, though we will be having decrease of pressure, but temperature will remain unchanged. Okay, so temperature will, T will be actually unchanged. So just if I want to say you, because what is happening, we already know that for ideal gases, enthalpy is nothing but function of temperature. So if enthalpy is not changing, it means temperature will also not change. Okay, so if we are having ideal gas in throttling process, then our temperature, though we will be having decrease of pressure, but temperature will remain unchanged, which will try to increase the specific volume of the gas. Okay, so which will try to increase the internal energy content. So in as a whole, we will be having actually the state of constant temperature. And if I talk about there are certain fluids for which what will be happening, if our pressure is decreasing, under that condition also we will be having a certain portion where actually temperature will increase upon decrease of pressure also. Okay, so these many details about the throttling process just I have shown you now at the moment. However, in more details we will try to see why this particular thing is happening. This thing we will try to see in our subsequent lectures. So there is one very important concept. That particular concept is known as Joule-Thomson coefficient. Okay, so Joule-Thomson coefficient is a very important parameter which actually governs that in a throttling process what will be happening. Means upon decrease of pressure, whether temperature will decrease or whether temperature will remain unchanged or temperature will increase. Okay, so it means what we are having, the characteristic of throttling process is that pressure will always decrease. Okay, but upon the decrease of pressure, what will happen to temperature? So that is something which is actually controlled by Joule-Thomson effect. Okay, so Joule-Thomson effect, we will try to, for understanding that effect, actually we require the knowledge of few more parameters, few more properties which will be coming into picture after the knowledge of second law of thermodynamics. So that's why once we are able to explore these other properties which are required to explain the Joule-Thomson effect, after that we will try to see the concept of Joule-Thomson coefficient, which explains that why upon decrease of pressure, in some cases temperature decreases, in some cases temperature remain unchanged, and in some cases upon decrease of pressure temperature also increases. Okay, so one of the typical example of throttling device you can find in our home refrigerators or air conditioning units. Okay, so now in this particular slide, what I had shown you, that we are having a pipe, and inside that pipe we have actually created some obstruction. Okay, so now this type of obstruction can also be created by partially closing few valves. So for example, if I have, say, arrangement something like this, I have some valve seat over here, and in this valve seat, say we are having some valve over here, and what I am doing while I am actually closing that particular valve, so I am actually partially rotating it. Okay, so if I am partially rotating this valve, so if I allow this small passage, so that will also act as nothing but a throttle. Okay, sometimes what we do, we also put some porous material in between our pipe. So if we are putting some porous plug in our pipe, so that porous material can also act as so through these pores we will be having actually significant pressure drop. So these pores will also act as nothing but throttling device. Okay, apart from that, one of the important device which is actually mainly many times can be seen our refrigerator and air conditioners is actually sudden contraction in the cross section of the pipe. Okay, so what we do, initially we are having a larger pipe, and then suddenly we are actually taking a very small pipe, and this particular small pipe is actually having dimension of the order of capillary tubes. Okay, so it is having dimension identical to that of capillary dimension. So this is also a device where what will be happening, while flow will be traveling from this bigger tube to the smaller tube, we will be having actually significant decrease of pressure. And this type of device can be seen in our refrigerators and air conditioners after the this one air conditioning units, after the condenser, where our saturated liquid refrigerant is actually expanded through this, and its temperature decreases at the same point of time. Some fraction of this liquid refrigerant converts into vapor also. Okay, so yes.
Sir, in this case, pressure always decreases and volume always increases, independent of Joule-Thomson coefficient.
Yeah, so volume will be increasing, and yes, volume will always try to increase. Okay, so I will try to explain you this in more details in our subsequent lectures while we will be talking about Joule-Thomson effect. Okay. Okay, so now we have next type of device. So till now, whatever the devices I have explained, in every of this device, in each of this device, actually we are having only single inlet and single outlet. Okay. Apart from that, we may have some devices where we will be having actually multiple inlets and multiple outlets. Okay. So one such device either we call as nothing but our mixing chamber. Okay. So in case of a mixing chamber, what will be happening? Say I have some control volume, and inside this control volume, say two different streams are entering. So one is entering with M1 dot mass flow rate, other one is entering with M2 dot mass flow rate, and both are then mixing inside, and then finally we are getting some outlet stream as M3 dot. Okay, now let me consider that inside this particular control volume, while stream 1 is coming, it is coming with enthalpy H1, M2 is coming with enthalpy H2, and M3 is coming with enthalpy H3. Okay, so now if I consider that the process inside this mixing chamber is nothing but completely adiabatic, it means across the boundary it is not having any heat interaction. So in that case, what will be happening? We will be finding first we have to apply the conservation of mass. So if I apply the conservation of mass, I will be finding m1 dot plus m2 dot is equal to m3 dot. Okay, so my m3 dot will be nothing but the summation of masses which are mass flow rates which are actually coming into the control volume. Okay, and then if I now apply the energy equation, so I am considering this process to be fairly completely adiabatic. So that's why I'll be having Q control volume across equal to 0. Work we are not having any in this particular process, and at the same point of time I'm considering that changes in kinetic and potential energies are also negligible. Okay, so now if I apply, by following all these assumptions, if I apply our steady flow energy equation, what will be happening? M1 dot into H1 plus M2 dot into H2 will be equal to M3 dot into H3, because this represents the energy inflow and this represents the energy outflow of this control volume. Okay, so finally I can say that my H3 is nothing but equal to M1 dot by M3 dot into H1 plus M2 dot by M3 dot into H2. Okay, so now what I can do, I can define, say that my M1 dot by M3 dot is say Y, and if I write M2 dot divided by M3 dot, so that will be nothing but equal to 1 minus Y. Okay, because M1 and M2 both are contributing to M3. So it means I can clearly say that H3 will be equal to Y times H1 plus 1 minus Y times H2. So now over here, if you try to see, Y is nothing but fraction of stream 1. Y represents the fraction of stream 1 in total mass M3, and this 1 minus Y represents the fraction of stream 2 in our total mass M3. So we are finding nothing but weighted mass over here. So whatever the final enthalpy we will be getting in this case, this final enthalpy will be nothing but equal to weighted mass average over here. Okay, so weighted mass average of the enthalpy is associated with each of the streams. Now, what is the typical example? If you go to your kitchen or bathroom, you will be finding the faucet of faucet is there, where what we are having some hot tape, and we are having some cold stream. These two are coming, these are joining, and finally we are getting some desired temperature of the water. Okay, so we try to get some desired temperature. How we are getting desired temperature? One of the stream we are having as nothing but hot, one we are having as our cold stream. So what we try to do, we try to control the flow rate of hot and cold stream. While we are controlling the flow rate of the hot and cold stream, that actually governs our desired temperature, whatever is required. Okay, for example, when we are feeling cold, at that time either we try to decrease the flow rate of the cold, or we try to increase the flow rate of the hot. Okay, so that is what we generally do in our kitchen faucet. Okay, apart from that, it may also happen that while we are having this particular control volume, because particularly during the cold season, you can see that if we are having our this control volume as hot, we may find that some amount of heat may go out of the control volume. Okay, so if some amount of heat loss is there, in that case what will be happening, my energy equation will take the form minus Q dot Cv plus m dot 1 into H1 plus m dot 2 into H2 minus m dot 3 into h3 equal to 0. And finally, I'll be finding that h3 will be equal to y times h1 plus 1 minus y times h2 minus q dot cv divided by m3. Okay, so in this case, now what will be happening? Whatever the I should have got based on the weighted mass average, whatever the enthalpy I could have got. So enthalpy will be, a final enthalpy will be actually decreasing by the amount QCV divided by M3. Okay. So this is like one typical representation when we are having heat loss. Okay, so this is physically also matching when we are taking certain amount of heat out in addition to the mixing. In that case, the overall enthalpy content of the outlet stream will be actually decreasing. And in the reverse case, if we add enthalpy, if we add heat, then obviously the enthalpy value will increase. Okay, so this is about the mixing process. Now almost we have tried to cover the majority of the devices which are encountered in engineering applications and which are particularly can be analyzed with the help of steady flow energy equation. Okay, now we are having certain devices which we cannot analyze with the help of our steady flow energy equation. Okay, so these devices are nothing but show variation with time. So their property actually varies with time. So such type of devices or such type of processes we call as transient or unsteady process. So we call few processes as transient or unsteady process. So what will be happening in transient or unsteady processes? In case of transient or unsteady processes, we will be having variation of property with time. We will be having variation of property within the control volume with time. Okay, so one of the example I can give you. So for example, if you have a glass, okay, so if you have initially glass is empty, so you will be having some mass m1. Say this mass, I am saying that glass is empty at nothing but time t equal to 0. Now if you are pouring some water inside, so while you will be pouring the water inside, what will be happening? Your during the process of pouring the water, our mass of this water glass will be changing, and say after time t equal to say something t2, after time t equal to t2, our glass is now fully filled with the water. So we will be having some another mass m, and that mass will be corresponding to time t2. Okay, so in this process now what has happened, we are having actually variation in the value of property with time. So these type of processes are referred to as transient processes. In case of transient processes, what we have, if we have to analyze these transient processes, obviously we have to employ integration between the two specified times where we have to determine the value of the property. Okay, and moreover for transient process, we cannot write that change in property with time equal to 0. So that's why while I'll be defining the conservation of mass for transient process, I have to write mi dot summation minus summation me dot, okay, or I am writing it as say outflow mo dot, that I have to write as nothing but d into mcv by dt, where we are, because we are having change of mass of control volume with time. Okay, now if I take my initial time as t equal to 0 and final time some value t at which actually our process has completed. So t equal to 0 is the time at which process is starting, and say the final time t is something, the value at which our process has actually ended. Okay, so now what I have to do, if I have to determine the values of properties during this particular transient process, what I have to do, I have to do integration. Okay, so let me integrate each and every term one by one. So let me first integrate the term given on right hand side. So what I'll be doing, I'll be doing integration 0 to d. I'll be doing integration of mass of control volume So this is the rate at which mass of control volume is changing, and this we have to integrate with time dt. So now obviously we will be having some relationship in between the rate at which mass is changing with time, and this we will be integrating with dt in between our initial and final states. Okay, so finally I'll be finding that mass of control volume at time t minus mass of control volume at time 0. So now let me say, if corresponding to t equal to 0, my thermodynamic state of the system is 1 or the control volume is 1, and at time t the thermodynamic state is 2. So I can simply say that mass of control volume at time t will be nothing but equal to m2 minus mass of control volume at t equal to 0 will be m1. So I can simply write m2 minus m1. So you can clearly see that this dmcv by dt was nothing but mcv dot. So while we have done the integration over time, our rate has converted into total amount of mass whatever has been seen during this change of state. So that's why now I am not writing any dot over here. So this is my amount of mass, and unit of this will be kg. Okay, so while I am writing dot, at that time we are having unit as nothing but kg per second, because system is actually undergoing through the process in flow. Then similarly, I have to now do the integration for sum of all the masses. So mi dot is the rate at which inflow of the mass is
Excuse me, sir.
happening. Yes.
But sir, you are putting limits 0 to t.
Yes.
And sir, these are the limits of time, not of DMCV.
Yeah. So what I am saying that this dmcv by dt will be having some function of time. Okay. So if it is having some function of time, obviously limits we have to substitute in terms of t only. Okay. Then what we will be having, similarly we have to integrate our summation of inflow masses. So this is summation of m dot I. This represents the rate at which inflow is happening, and this I have to integrate over time dt. So if I do this integration, I'll be finally finding simply as summation of mi. So my dot will be actually taken out of the integration, because this mi dot is nothing but mi by dt. Okay. Similarly, if I integrate summation of m dot o over the period dt, and this within the limits whatever are specified. So this also will be my nothing but sum of all the masses which are actually going out. Okay. So instead of the rate term, now what we will be having? We will be having actually the amount of mass during the period. Okay. So that's why my final equation, conservation of mass for transient process, will be sum of all the inflow masses minus sum of all the outflow masses will be equal to mass corresponding to state 2, which represents the final state, minus mass corresponding to state 1, which represents the initial state at which actually our process has started. Okay. So similarly, if you do for energy equation, obviously now I will not show the integration of one by one term, but what I will be doing, all together I'll be finally giving you the final equation. Okay. So for transient process, if I have to write down my conservation of energy, I can clearly simply write as sum of the amount of energy which is associated with the net amount of energy, a net amount of heat transfer associated with the control volume. So sum of QCV minus sum of work associated with the control volume during the process time. So that we are doing after integration. Okay. Plus sum of mi into, say, ei is my total energy content, minus sum of O into EO as my total energy content. That will be equal to nothing but energy at state 2 minus energy at state 1. So E2 minus E1. Okay. So this type of process for which we are having variation of the property with time, we call that process as nothing but our transient process. And for this transient process, what will be happening? We will not be having the equation in rate form. Rather, we will be having actually total amount during the period for which process has taken. We will try to obtain the integration. Okay. Now, let me just give you one example of a transient process, and let us try to apply our equation for this transient process. Okay. So what I am doing, I am considering that I have one well insulated tank. So this tank is, say, completely insulated. So I have an insulated tank, and in this insulated tank we have some valve over here, and this particular valve is now connected to certain line. Okay, and say in this line we are having some a stream which is actually flowing. So some medium is actually flowing inside this line. Okay, so while this medium will be flowing inside this line, during that time, say it is having some enthalpy Hi. Okay. Now, if you talk about the tank, let us consider that at the initial point, this valve is closed and this tank is actually having absolute vacuum. So, what we are considering the tank is having absolute vacuum. Okay. Now, what I want to do, whatever the control volume which I want to analyze, that only includes the medium. I am not considering tank wall as my control volume, part of the control volume. So what I am considering, only the medium, whatever I will be having inside this tank, that is only my control volume. So that is only the thing which I will be actually trying to analyze. Okay. So this is my initial state. So corresponding to this initial state, say this initial state is at time t equal to 0. So corresponding to this initial state, if you try to see, our mass of the system m1 equal to 0, because we are having absolute vacuum inside. At the same point of time, our energy content of the system E1 is also equal to 0. Okay, so that is something which we are having initially. Now what we have done, after that we have actually opened this valve. So now valve is opened. So once we have opened the valve, what will be happening? This particular fluid from here will try to flow into the tank. So we will be having flow of fluid into the tank. And this flow of fluid into the tank will be happening until our pressure inside the tank is reaching equal to that of pressure in this pipeline. So at this line, we will be having certain pressure. So until we are having the pressure here and here are same, till that time flow will be happening. Or another thing could be that I am actually closing this valve. Okay, so that will be my final state. So say I have allowed this process to happen for time t, and during this time t we are having accumulation of some mass, and obviously while mass has come, that mass will be carrying certain amount of energy also. Okay, so it means in the final state, now final state is my after time t. So corresponding to the final state, I will be having certain amount of mass m2. Okay, so that is clear that we will be having certain amount of mass, and at the same point of time we will be having certain amount of energy content E2 also. Okay, so we will be having some amount of energy content E2 also. Okay, so now let us try to apply our mass and energy conservation equations for this particular transient process. So if I apply the mass conservation equation, what will be happening? We have to consider sum of all the masses which are entering. So we are having only single mass stream. So single stream through which our mass will be entering. So let us consider that mass entering is equal to mi. Okay, so now I cannot write m dot I. What I have to do, obviously mass will be entering with some rate only, but that rate we are observing for some time 0 to t. Okay, and now what we are doing over here, we are actually providing the final amount which has entered during time 0 to t. Okay, so what I'll be doing, I'll be writing over here m of I. So this is my mass inflow. This is the inflow of mass during time 0 to t. So from time 0 to t, what amount of mass has entered, that we are actually writing. So that is my mi. And if we see our control volume, in our control volume, we are not having any exit for the mass. So if we are not having any exit, then minus MO will be equal to 0 because there is no outflow of the mass. And this will be equal to nothing but M2 minus M1, where M2 is the mass corresponding to the final state, M1 is the mass at the initial state. I have already told you that initially our system was in absolute vacuum. So initial mass of the system will be equal to 0. Okay, so M1 is 0. So that's why I'll be only having M2. So from this particular equation, I can say that whatever the amount of mass has entered, that is nothing but equal to our overall mass of the system. Okay, so this thing at the final state. So this is the thing which we have seen from our continuity, from our mass conservation equation. Now let us try to see the conservation of energy. So if I apply conservation of energy, I'll be having QCV during time t. So QCV will be 0 because we are not having any, we are having perfect insulated boundary of the container. Then work also during this time will be equal to 0. Now work is also 0. Then we are having some inflow of mass. So inflow of mass is Mi, and enthalpy of this I have taken as nothing but Hi. Minus MO into HO is 0 because we are not having any outflowing stream. Now that has to be equal to nothing but E2 minus E1. Now E1 we already know from our energy conservation corresponding to state 1, what we are having corresponding to state 1, you can clearly see that our E1 is equal to 0. Okay, so E1 is equal to 0 because we were not having any mass inside. So E1 is 0. Now E2 I can write as my final mass of the system. Now E2 will be nothing but at the final mass, whatever the energy which is associated with this particular system. Okay, so corresponding to the final state, we are having M2 mass inside the system. So I'll be having M2 as mass times we will be having E2. And now we know E2 is nothing but my specific energy. So this, dot will not be here. It will be only M2 because we are having final mass. Okay. So M2 into E2, where E2 is my specific energy content. So this we know that M2 into E2 is nothing but U2 plus V2 bar square by 2 plus GZ2. So now let's say our elevation is negligible. So this part will be 0. And kinetic energy, obviously our gas is actually coming into the control volume, and inside the control volume, inside the container, it will be almost stationary. So I'm considering kinetic energy also to be 0. So finally, if you try to see, we will be finding M1 into Mi into Hi will be equal to M2 into U2. Okay, and this, from our conservation of mass, we already know that Mi is equal to M2. So it means finally we will be finding that Hi is nothing but equal to U2. So it means if we are having this tank filling process, okay, and if tank filling process is happening under the adiabatic conditions, so whatever the final state of the system we will be having, we will be finding that the final internal energy of the system will be equal to that of the enthalpy of inflowing stream. Okay, so this is a typical example.
So why kinetic energy is equal to 0?
Kinetic energy, because in final state 2, our gas has entered inside the tank. Okay, so in final state, actually we have once again closed the valve. So it means there is no bulk motion of the medium inside the tank. Now gas is in the almost in the as a whole. Obviously molecular level will be having some translations and rotations. Because of these molecular rotations and translations, we are having the content in terms of internal energy. However, we are not having any bulk motion of the medium. So because we are not having any bulk motion, so that's why kinetic energy will be 0. Okay.
Sir, why GZ2 is 0?
Why?
GZ2 is 0.
I am not getting your question.
So why is potential 0?
Oh, potential. So we are considering that with reference to, please mute your microphone first. Yeah. So what I am saying that with reference to our ground, whatever we are considering the reference of 0 potential energy, with reference to that, our elevation of the control volume is negligible. Okay.
Sir, why is MO into H 0?
Because MO represents the mass of outflowing stream. Okay, so we are not having any stream which is going out of this control volume. So that's why MO is 0. Okay.
Sir, if there is no change in potential, then why should the water fall in the first place? Because only there is a reduction in potential, the water falls right into the
Yes.
bucket.
Yes.
If
Yes.
there is no change, then it should not fall.
See, I am not getting your question now. It is not clearly audible. So what you do, if you are having any specific query, let us discuss it during our doubt clearing session. Okay.
Sir, what can we finally conclude from this?
This is nothing but what I have done. I was having a very specific type of process for which I considered insulated boundary and initially as absolute vacuum. Some hypothetical conditions I have considered. And under these hypothetical conditions, I have tried to show you the application of transient mass and energy equation. Okay, so this is a transient process for which I have explained you the conditions of energy and how the mass and energy equations are actually applicable. So I have just demonstrated an example. So for this particular example, we can say that our enthalpy of the incoming stream is actually equal to that of the internal energy of the final system. Okay. So that is something which is very, very specific to this particular example. The sole motto of showing this example is to demonstrate how we can solve the transient processes. Okay. So while we are dealing with the transient processes, there are certain things which our process should satisfy. So some of these things are, so whatever the inflowing and outflow stream we will be having. So if we are having the inflowing and outflowing streams, so their thermodynamic state should not change. Okay, so this is one very, very important assumption. For example, what is the meaning of this? As I have told you in previous case that we are having a tank and we are having some valve over here, and then over here we are having some stream coming with enthalpy Hi. So if it is coming with enthalpy Hi, it means this is nothing but Hi represents the thermodynamic state of this stream. Okay. So while this transient process is happening, our thermodynamic state of this particular stream should not change. Okay. Because we are considering that while we integrate, we only are considering the variations in the mass flow rate. Okay. So we may have variation in the mass flow rate with time, because while we are obtaining the overall Mi, that we are doing as integration of Mi dot with time dt. So obviously if we are having the variation of mass fluctuation with time, that can be accounted in this overall mass calculation equation. However, we are not doing the integration for finding the change in state of the thermodynamic property. So that's why while we are analyzing our transient processes, we should not have inflowing and outflowing stream whose thermodynamic state is actually changing. So their thermodynamic state during the entire process should remain constant. Okay. So now with this topic, I conclude our discussion of first law of thermodynamics for both the closed as well as the open systems. And for closed system, already I have given you 2 assignments. Now related to first law of thermodynamics for open system, I'll be soon uploading one assignment. Okay, where you can practice the problems related to these concepts. Now let us try to see that what are the limitations of first law of thermodynamics. So there are certain limitations of first law of thermodynamics, because of which we have to go for another concept which is referred to as second law of thermodynamics. Okay, so what are the limitations of first law of thermodynamics? That let us try to see. Okay, so these limitations we will try to see with the help of some examples. So the first point is that when we talk about first law of thermodynamics, we are not concerned about the process whether it is feasible or not. Okay, in terms of first law, our main concept comes into consideration that energy conservation should satisfy. Okay, so total amount of energy should remain conserved, and in the different thermodynamic process, one type of energy can change into another type of energy. Okay, and if overall energy content is remaining constant and we are having actually changes in the different kinds of energies while the thermodynamic processes are happening, that is all acceptable. Okay, it doesn't tells us that what are the processes which are not possible. For example, if I give you a typical example of a pedal wheel, so say we are having a container and this container is initially, say, well insulated. Initially it is well insulated, and now we are having some pedal wheel over here. Okay, so over here we have some pulley, and then we are having some weight which is actually attached to it. So this is, say, the initial position of the weight. Now at this point we are having, say, thermodynamic state of the system as state 1. Okay, now what we have done, we have allowed this weight to move downwards under the influence of gravity, and say finally this weight has reached to this position W, and during this we have change in height of the weight as h. Okay, so obviously what will be happening now, we will be having actually the what while this weight is moving down, our this pedal wheel will be actually rotating. Okay, and this pedal wheel now will be doing certain amount of work on our medium. So from the pedal wheel there will be certain amount of work which will be done on our medium, whatever we are having inside. Okay, so now in this case what will be happening, you will be finding that pedal wheel has done work equal to that of the change in potential energy mgh, and this much work, this much of energy has been added into the system. So once our weight has moved through height h, we will be finding that in our final state, in our we will be having actually increase in internal energy content of this control volume. So when we will be having increase in internal energy content, our state will be something else, state number 2. Okay, now can I do the another way? Means I will transfer this internal energy to my weight, and because of to this my pedal wheel, and because of that my weight now will be actually raised through the same height h. Is it possible?
No.
No, sir.
So, but thermodynamically, if you see, as per the first law of thermodynamics, what we have done, we have supplied mgh amount of energy, and that mgh amount of energy has changed. If I say m is my mass of the system, say ms as my mass of the system, so that has changed the internal energy by amount u2 minus u1. Okay, so as per the first law of thermodynamics, it should happen that if I supply ms into u2 minus u1 amount of energy to my pedal wheel. So if this much amount of energy I supply to my pedal wheel, okay, this should raise our weight through height h. Okay, so we should have mgh amount of work done. Okay, so if you try to see from the first law point of view, this equation is actually completely valid. Okay, because first law of thermodynamics says that we may have conversion of any kind of energy from one form to another form. Okay, however, we should not have any destruction of the energy. So if we are able to satisfy the conservation of energy, so we can do any type of conversion. So it means we have seen that this previous process, it was possible and it is actually satisfying the first law of thermodynamics. Now this second process also, it is possible, but it does not satisfy, it is not possible, but it also satisfies the first law of thermodynamics. Okay, so it means first law of thermodynamics does not tell whether process is feasible or not. Okay, and moreover, in this particular process, what was happening, in one of the direction it is possible and in second direction it is not possible. So it also does not gives us information about direction of the process. So in what direction our process should happen, that information also we cannot get from our first law of thermodynamics. Okay, apart from that, it only talks about quantity of energy. First law of thermodynamics only talks about quantity of energy, that we are converting some quantity of energy from one form to another form. Now, which form of that energy is having highest potential for doing some useful amount of work, that is something which is referred to as the quality of work. So we cannot infer anything about the quality of the work from this first law of thermodynamics. Okay, so these are a few limitations of first law of thermodynamics. Apart from that, we are having many processes with the help of which we can explain these limitations. So I'll take up this topic once again in our next lecture. Now I'll stop at this point.